Hey everyone, Mr. H here. We're going to continue with 7.6 notes, page 3. So the focus on this page is finding all exact value solutions or just all solutions in general. Instead of specifying a degree, they use that word all, which means there's an infinite number of solutions and we've got to figure out a way to write that. So the first step on number 15 is the same as we've been doing. So we're just going to isolate that trig function. And then think about the unit circle and what values the sine theta is equal to 1/2. So there's two of them. There's 30 degrees from quadrant 1, where sine is equal to 1/2. And there's also quadrant 2 at 150 degrees. Get the sine equal to 1/2. And then any coterminal angle to those would also be a solution, right? Because we're not restricted just to one revolution, right? There is an infinite number of revolutions. So the way to do that is I would just add any multiple of 360. So I would do a 360n, where n is any integer. Same with 150, add any multiple of 360 and you get a solution. So all your solutions for theta are those. So theta equals all of that. So that's a long list, but that's the way to do it, where again, n is any integer. Sometimes I don't write that, just assumed, but to be clear, n is a whole number, positive or negative. So that gives you every answer. Okay, so you'll be, adding those on. How about for tangent? Tangent for a negative root 3, right? So negative in quadrants 2 and 4, right? Let's focus on quadrant 2 for a minute. So in quadrant 2, where do you get tangent equaling to negative root 3? Remember, it's the y over the x, right? So where y is root 3 over 2 and x is 1/2, that's happening up there at 120, right? So we have 120 degrees for a solution in quadrant 2. What I'm doing again is visualizing that unit circle. So right here, right, where the tangent y over x is root 3 over -1 or negative root 3. That leads me to that angle of 120 or 2 pi over 3 in radians, but they want degrees on this one. Right. Okay, whoa, back to this one. Okay, now I could go and find the quadrant 4 solution, but tangent's a little different than sine and cosine because the period of tangent is pi, or tangent repeats itself on intervals of pi or 180 degrees. So if you add 180, you get another angle that's a solution for tangent, and keep adding any multiple of 180 for tangent and you get another solution. So for this one, I'm just going to add 180 n, and that will be my solutions. Okay. You could do it with 120 plus 360 n, but then go get the quadrant 4 and then that angle plus 360 n, that would work. But tangent actually is a little simpler because of the more frequent period. Okay, how about 17? Let's see, looking at that one, looks like I can first factor out a cosine. So I'd have cosine theta. If I do that, I'll have sine theta plus 1. Right. And then set each part equal to 0. Okay. And then solve for the trig function. Cosine theta is already isolated. Sine theta isolated will be equal to -1. Okay, now we're going to the unit circle and thinking about, okay, where does the cosine equal 0? Well, that's when the x value is equal to 0. So that's at the top of the unit circle and at the bottom at 90, and then 270, and then back up to the top, back down below, back up to the top. Every interval of 180 degrees, you're going to be back at a solution, right? So my first one is 90. And then if I add any multiple of 180, I'm going to be back at the top or the bottom of that unit circle. Right? So that's the branch for cosine equals 0. 90 degrees plus 180 degrees times n, where n is any integer. Now, how about for sine theta equals -1? Well, that only occurs in one spot. That's at at 270 degrees. You get that y coordinate equal to -1 on the unit circle. So 270 is certainly an answer. But that's the only place. So the only way to get back around to that spot would be add a 360, right? So 270 plus 360n, right? And that's that branch. Now, interesting to note, all of these are generated by that, right? So all of these are actually included because these have all of those values that are down at the bottom at 270, right? So this is a little bit repetitive. In general, I could just specify this. This gives me all of them. Gives me everything for the cosine theta equals 0, and then also includes that, right? So a little crazy there, but my final answer would just be the 90 plus 180, and that gives me every solution. Okay, all right. How about all exact value solutions in radians? How does it look in radian mode? So solve for sine x. I would bring the 1 over and then divide by √2. So where does sine equal a negative √2/2? That's quadrants 3 and 4 where sine is negative. So if you look on your unit circle, you'd have in quadrant 3, that's that 5 pi over 4. And at quadrant 4, you get 7 pi over 4. And then any coterminal angle to those would work. So if you add 2 pi, right, 1 full revolution, it's equivalent to 360. Add 2 pi, you get another solution. So the way you would write that, typically you'll see it as 2n pi. Just kind of stick an n in there, where n is any integer. And that would be, 1 revolution, 2 revolutions, 3 revolutions added to that angle that generates them all. Okay. For number 19, how about cosine x equals -1? Well, the only place on the unit circle where cosine x equals -1, or again, that x coordinate on the unit circle, -1 would be at pi. Right, so I know I have an answer at pi. And that's the only place on that first go around of the unit circle. So to get back around to that solution, I would have to add a multiple of 2 pi. So multiple of 2 pi, I'm writing as 2n pi. Right. And there would be my final answer. Okay. Okay, let's try number 20. So this one, all solutions in radians, and we have a quadratic trinomial. It doesn't factor. So we're going to have to use the quadratic formula to start this one off. So we're going to have sine x equals -b, which would be a +8, plus or minus the square root of b squared, which is 64, minus 4 times a, which is 2, and c, which is -1, all over 2a. Okay, and then simplifying that radical, we'll have square root of 64 plus 8 all over 4. So that's going to bring us to 72 over 4. And then I'm going to do 1 for the plus and 1 for the minus in my calculator. So let's get the plus. So if you want to check my work on this, that would be good. I'm doing just 8 plus square root of 72, hit enter, and then divide by 4, and that's going to give you 4.1213. And then if I do a minus, what do we come up with? We're going to get -0.1213. Okay, so those are my two values. Now, that's what sine x equals. Anytime when you're doing the quadratic, if you've got a trig function like sine or cosine equal to a number, that number has to be between 1 and -1, or else there's no solution, which means if you get a number bigger than 1, you can just toss it out. Okay, so that's good. We only have to work with this guy. So continue on. Now I've got sine x equal to negative 0.1213. Okay. Sine is negative in quadrants 3 and 4. So that's where my answers are going to come from. But the first thing I got to do is get a reference angle. And the reference angle is going to be sine inverse of that number, just without the negative. Right? And now in your calculator, you're doing sine inverse. Make sure you're in radian mode. And this is going to be approximately 0.1216. Okay, there's your reference angle. Now we've got to go to quadrant 3 to get the actual answer. And in quadrant 3, that's past pi in radians. So you're going to add pi to this. So we're going to do pi plus 0.1216. Right. And so I already have it in my calculator. I'm just hitting plus pi. And then I'll do the proper rounding to 3 decimal places. That's 3.263. Okay. The other answer is in quadrant 4, where you would do 2 pi minus the reference angle. So do that with your calculator, 2 pi minus 0.1216, 6.162. Okay, and those are the answers between 0 and 2 pi. Now we've got to deal with all. So if it's in radians and we want all, you know, to get another answer, it's just another revolution. So any addition of 2 pi. So I'm going to just add a 2n pi for as many revolutions as I want, right? And those are your x values. So we have 2 branches of that final answer. Okay. And that's it for that one. That's a good stopping point. So we'll continue with problem number 21 in the next video. Send questions my way if you have any, and hope all is well. Talk to you later.